Hello everyone, here is the lesson for 7.3 that deals with the sampling distribution of proportions. So let me do a little explanation first and then I will do some examples with you. So a sampling distribution of proportions occurs when you are talking about data that is countable as opposed to measurable, which was what we were doing for 7.2. We're talking about sampling distribution of means. This one we're talking about distribution of proportions. For example, if you are talking about the number of items satisfying a particular preset condition, like if you're talking about the number of customers in a randomly selected sample who prefer to use Kudo to tell us or to Bell, the proportion that we're talking about there is what we're looking at. Okay, but we're looking at that proportion for the population of all customers. Or if you're talking about those who will vote for a particular party, the Liberal Party or the Conservative Party, right? That proportion is what we're looking at. Or if you're looking at the number of students who live off campus as opposed to those who live on campus, right? That would be the type of things that we're looking about. Data that is countable, okay, is what we're thinking about. And to calculate the proportion, the sample proportion, the formula is as shown. It's p hat, which is equal to x divided by n. X is the number of items in the sample that satisfies the condition we want, and n is the sample size that we're looking at. Okay. Now it turns out that just like the central limit theorem that we discussed for 7.2 ensured that the sampling distribution was normal, the same thing is going to be true here as well, right? So the central limit theorem is true for proportions too, and it goes as follows. It says that if samples of size n are randomly drawn from a population that has a proportion p, that's population proportion p, and standard deviation square root of pq over n, then sample proportions p hat are approximately normally distributed for sufficiently large sample sizes n greater or equal to 30, regardless of the shape of the distribution. So it's kind of like the same thing that we discussed for 7.2, except that this time we are not talking about the sample means. We are talking about the sample proportions, okay, which is the p hat. You calculate p hat. Like we did for 7.2, there is the appropriate z-scores. So if you are going to take the sample proportions and you want to standardize them into the z-scores, the formula for that is as shown. Okay, it's right here. Z is equal to p hat minus p divided by the square root of p times q over n, where p hat is your sample proportion of interest, your p is the population proportion, and q is the difference between 1 minus p. Okay, so it's just a complement of p. And the standard error of the proportion, the formula for that is as shown. Okay, that's the standard deviation. Okay, it's just called standard error. It's the square root of pq divided by n. Okay, so that's what we're going to do here. I'm going to show you a couple of examples, and then I'll get you to try one, and then you can go and do some stuff on Wiley plus. So, for example 1, if 10% of a population of parts is defective, what is the probability of randomly selecting 80 parts and finding that 12 or more parts are defective? So in this question, you can see that it talks about the proportion of parts that are defective. So it's either the parts that are defective or they are not defective. 10% are defective of all the parts. So that's your population proportion. And according to our central limit theorem, the sample size here that they're talking about is 80. So we know that the distribution of proportions will be normal, like this. So the population proportion is 10%, it's right in the middle there. And the complement of that is Q, that will be 90%. The sample proportion that for this question, 12 out of 80 is the parts that we're talking about, right? We want to find the probability that 12 or more are defective. So 12 is that threshold. 12 over 80 is 15% or 0.15. So that is the sample proportion. And as far as our picture goes, the area or the region of interest is the one I've shaded here in red. Your 15 or your 0.15 sample proportion is as shown. And of course, our table of values will only give us the area that I shaded in black in there. You use our Z tables for that one. So the corresponding Z score, when we're going to standardize 15% for the proportion, the formula that I showed you that before, is what I have in here right now, is P hat minus P divided by the square root of PQ over N. So if we substitute all the values that we have in there that we obtained from the question, we know that P hat is 15%, P is 10%, and Q is 90%, and N is 80. So if we substitute and calculate in our calculators, Z sub P hat will be 1.49 standard errors. Okay. So now all we're going to do now is to find the probability that X is greater than 12 defective parts, which is the same thing as saying that the probability of that the sample proportion is greater than 0.15, and then that's the same thing as the probability that the sample proportion or the Z score is greater than 1.49. So in your table of values now, if you look for 1.49, you would get the area that I shaded in black in the picture over here, right? This area here is what you're going to get for your 1.49 in your Z table, which if you do, you will get 0.4319. Subtract that from 50% because half the normal curve is 50%. You will get 0.0681. So the probability that that out of 80 parts, you will have 12 or more that are defective if the population proportion is 10%. That probability is about 7%, 0.0681. I hope that's clear. Let's do another example. Example 2. According to a study by Ipsos Reid, 40% of Canadians rely on doctors for drug information. Suppose a random sample of 600 Canadians is taken. What is the probability that less than 180 of them rely on doctors for drug information? So again, in this example, we are not told what the distribution is originally. So we're going to have sample size. You can see the sample size is 600, right? So according to Central Limit Theorem, we're good, right? The sampling distribution of the proportions will be approximately normal. So the picture we're looking at looks like this. The distribution is normal, the population proportion is 40%, and Q is 0.6, if you subtract that from P. And we are looking for a sample proportion of P hat, which is 180 over 600. That is 0.3, that's 30%. And that's way to the left over there. You'll see why I drew it in that way in a sec. Okay, so the Z score that we need will be calculated using our Z score formula for proportions. If we calculate Z score for 0.3, you will see that it's -5. -5 standard errors. That's why I drew my picture the way I have it here, right? You can see that's way to the left, like it's way over there. Okay, so if we use our normal distribution table now to figure out what we need, our normal distribution table, that's probability that X is less than 180 people in a sample of 600, which translates to the probability that the sample proportion is less than 30% or 0.3. That means you are talking about probability that your Z score is less than -5, right? In your Z table, if you look at -5, right, you will see a number that's very, very close to 50%. So essentially everything is in there, you know, right? So 0.5 minus 0.4999997 is just something very small. That means that probability is 0. So that means that it's almost an impossibility to find 180 or fewer people in a sample of 600 that do not rely on doctors or that relies on doctors for drug information if the population proportion is 40%. It's just not likely, right? Most it will be the scenario is that most Canadians or a lot of Canadians do rely on doctors for drug information. So that's how you would do that one. I have one more example to show you before you try one yourself. Number 3, candidate Liu believes he will receive 0.55 of the total votes cast, so that's 55% of the total votes cast in his riding. However, in an attempt to validate this figure, his pollster contacts a random sample of 600 registered voters in the riding, and the poll results show that 298 of the voters say they are committed to voting for him. If he actually has 55% of the total vote, what is the probability of getting a sample proportion this small or smaller? Do you think he actually has 55% of the vote? Why or why not? So this is a nice example. This guy thinks, a lot of people love him. And then he goes to verify that, he goes and takes a sample, right? So we know that the distribution will be approximately normal because the sample size is greater than 30. So we have the population proportion that he thinks he has is 55%, and we can calculate Q as shown. The sample proportion is 298 over 600. I calculated that to the thousandth place, 0.497. And then we're going to use that to figure out what we need. The z-score, corresponding z-score, is negative 2.61. So in the picture there is to the left, you can see that shaded red area is what we are looking for. And if we calculate this using our z tables, the probability that in a sample of 600 voters, where the population of support for him is supposed to be 55%, that probability of having less than 298 or less, is as shown, 0.0045. Now, what does that mean? What that means is that it's very unlikely that you will have fewer than 298 people supporting you in a sample of 600 voters if you actually have 55% support in the population. It's very unlikely that a sample will produce less than 298 of people who support him. So I think this guy is deluded. Okay, it's very unlikely that he has 55% support. That is what that means. Okay, all right. I hope that these examples are a bit clear to you. You can try one example by yourself now. And what I would like you to do is you should pause this video now while you try this example. And when you finish, you can continue the video to see what I have done. So please pause the video now. Okay, so what did you do? So I'll show you what I did. Sorry, let's read the question. So the question says, suppose that 33% of people in a city commute by public transit. In a random sample of 78 people from this city, what's the probability that less than 30 people will commute by public transit? So the picture we're looking at looks like that. The population proportion is 33%, and you can calculate Q from that is 67% or 0.67. You want to find the probability that in a sample of 78 people, 30 or fewer commute by transit. The sample proportion is 30 over 78, which is 0.38, and we can calculate the appropriate z-score, z-score p hat. That will be 0.94 if you calculate that properly. And so the area we're looking for in our picture is as shown. Okay, right, and we can use our normal distribution table to calculate. Now, because your 0.33 or your 0.38 or your sample proportion is to the right of the population proportion, you will have to add 50%, okay, to whatever you obtain from your Z tables. So if you look for 0.94 in your Z table, you will see that your area is 0.3264, which if you add to 50%, that probability is 0.8264. Okay, so to answer the question, the probability that fewer than 30 in a sample of 78 will be using public transport is about 83%. Okay, so I hope that is clear. You can watch the video again if anything is unclear there. The next video that I'm going to put up will be for chapter 8.